Hello, this is Group 2 of me588 for winter 2021, and we are doing the assembly analysis of the scissor jack from McMaster. On the team, we have myself, Michael Getty, Braun Landis, Jeremy Goldhawk, and David Stanton. The scissor jack is used to slowly raise and lower heavy objects. The most common use for it is to lift a car while changing a tire. It has a minimum height of 4 inches and can lift 250 pounds and a max height of 9 inches, which can withstand 3,000 pounds. The screw is threaded in both directions, which allows for the jack to move up and down. When turning the screw, the middle linkages of the assembly will either expand or contract to one another, which allows the top plate to move up and down. Here we show on the left is an assembled view of the scissor jack in its maximum height, which can withstand 3,000 pounds. This is most likely when the jack will be in use. And on the right we have an exploded view where you can see all of the linkages and fasteners that are used to assemble the scissor jack. Here's another exploded view, this time showing each individual part and what it is. Starting at the bottom, we have the base, which is stamped and brake pressed. The base then connects to the links. There are 3 different kinds of links and 4 of each type, 2 on each side. These links are stamped into shape. Next, the links connect to the threaded axles and the screw, which are both made on the lathe and the mill. And finally, we have the top carriage, which is also made by stamping and brake pressing into shape. All of these are connected by the pins, which is made on the lathe, and all of the objects are made out of steel. This slide shows our KC1. It bounds the maximum height of the jack at 9 inches as the optimal operation height. This KC is constrained in all 3 rotational directions, and in the X and Y translational direction, it is only free to move on the Z-axis. The highest operational weight is found at this height because of the efficient loading transfer through the linkages. KC2 requires that the top plate of the scissor jack be perpendicular to the normal of the bottom plate. Essentially, this means that the 2 plates must be parallel to one another. KC2 is determined at the maximum height of 9 inches. This is for both functionality and safety that the jack should be parallel, and it should also be used on parallel surfaces so that the object that you are lifting does not slip off. KC2 is constrained in all 6 degrees of freedom within the assembly frame, and KC2 can be pushed out of range if any of the linkages have variation in them.
Here you can see the datum flow chain for the scissor jack assembly that we've been working with. In the upper right hand corner, you'll see an image of the assembly with a global coordinate system imposed upon it. This is the coordinate system that we will use to describe the degrees of freedom of each part, as well as the degrees of freedom that are constrained by each mate. In this coordinate system, KC1 is the Z position of the top, whereas KC2 is the angle formed by the rotation about the Y-axis of the top. This slide shows the degrees of freedom that are constrained by each mate. In our assembly, there are several pin joints between links. We found that a pin joint constrains 5 degrees of freedom and has 1 degree of freedom that is unconstrained. The unconstrained degree of freedom is the rotation about the Y-axis, whereas the X, Y, Z translation and the rotation about the X and Z axis are fully constrained. It is important to note that the center of mass of the links translates in the X and Z direction. However, that translation is a function of the rotation about the Y-axis, and as such is constrained. The other type of mate that occurs in this assembly is the mate between this threaded rod and the screw. Obviously, the screw is constrained in the thrust direction by the threads. However, it is free to rotate about the thrust axis and is constrained radially in translation, and as well as it cannot rotate about the radial axes due to the nature of the threading. Another important thing to explain is this pink part that is threaded that the screw goes through. It functions, I just described the mating conditions for that screw, but on either end, it also functions as a pin joint to connect the links together, and is constrained as the pin joint as I just explained.
We will now discuss the delivery chains for each KC, using the datum flow chain that David described before. For KC1, we care about the Z constraint between the base and the top. Using the datum flow chain, we highlighted each possible delivery chain from the base to the top that constrains Z. As you can see, there are many different paths, which shows that KC1 is very overconstrained. For KC2, we care about theta in the y direction between the base and the top. Although each delivery chain does not show a chain of mates in the theta y direction, it shows a chain of mates in the x and z direction. To satisfy theta y, we take a different method, where if we had two mates in the x that constrain the x and two mates that constrain the z, then theta y between the base and the top would be not over-constrained and not under-constrained. But since there are four mates in the x and four mates in the z that go between the base and the top, KC2 is also overconstrained. We do not suggest any redesign to eliminate these overconstraints because we believe it was part of the design intent to help with the strength, as screw jacks need to lift heavy loads. Also, no fixtures were necessary in these delivery chains in the assembly of this screw jack.
Assembly sequence 1 sees the manufacturer assemble the side structures first, before mounting them to the interior mechanism and finally the top and bottom plate. On the left, you see the assembly tree for sequence 1. Please note that for both sequence 1 and sequence 2, joining pins are attached at each joint but not shown in the diagrams due to visual complexity. Additionally, for sequence 1, subassembly 223344 is repeated twice for each side of the jack before being mounted to the interior mechanism and finally the top and bottom plate. Assembly sequence 2 sees the manufacturer starting from the bottom and working their way vertically upward to the top plate. As you can see on the assembly tree to the left, the manufacturer starts with the bottom plate and the interior-most strut before working upward and outward at each step and finally attaching the top plate. Here we have our assembly sequence analysis. When talking about the ease of delivering KCs, both sequence 1 and sequence 2 are relatively similar, and we don't foresee any difficulties in this process. When looking at the ease of transferring and handling parts assemblies during the process, sequence 1 is better than sequence 2 due to the fact that the only reorientation step needed is when moving from the side assemblies and attaching them to the top and bottom plate. Sequence 2 is much more difficult as the part is unstable until fully assembled. When looking at the need for a fixture, sequence 1 is much better than sequence 2. Sequence 1 allows the use of a fixture to make each side subassembly before attaching them to the top and bottom plate. Sequence 2 is much more complex due to the nature of assembling upward. The fixture, if used, will require new pieces at every single assembly step. When looking at the ease of fastening and joining, each joint on sequence 1 is easily accessible and there are not any required modifications or special fixtures needed. Sequence 2 might have some issues when looking at attaching the joints in the middle between the two side pieces. This is due to the fact that each side piece is assembled on the bottom plate at the beginning and not separately like you have in sequence 1. Similarly, when testing their functions at each assembly step, sequence 1 is better than sequence 2. Once each side assembly of sequence 1 is completed, functional testing of that piece is possible. Sequence 2, however, requires the entire product to be assembled before any steps can be tested. Ease of assembling subassemblies in parallel. Sequence 1 is very well thought out and considered for assembly in parallel. This is due to the fact that each side structure is assembled separate from the top and bottom plate before being attached in the final assembly step. Sequence 2, however, is much more difficult and quite linear in process. Consequently, you can see at the bottom, our total for sequence 1 is 15 out of 18 and sequence 2 is 8 out of 18. This means that sequence 1 is the best choice for our assembly sequence.